Hello AP Chemistry and welcome to almost being done with chapter 19. Okay, so Gibbs free energy. So before we talked about how at the very beginning of chapter 19, right, we talked about how some things are spontaneous at certain temperatures and not at certain temperatures, right? And in the last chapter, we talked about how exothermic and endothermic is a huge indicator about the favorability of a process, right? Chapter 5 had that little section that sort of alluded to thermodynamic favorability and how a lot of exothermic processes happen spontaneously, right? Happen on their own, but not all exothermic processes happen on their own, which means that we have to have a way to tie together enthalpy and entropy, and Gibbs free energy is a quantity that allows us to do that. Gibbs free energy is a state function, right? So it works just like our enthalpy stuff did, right? And we have to have, and so this is what ties these together. So we have the idea that delta G is equal to delta H minus T delta S, right? We also have our standard version. Okay, now they really mean the same sort of thing, right? Except this means that we're talking about all of my quantities at standard conditions. So 1 molar, right? 1 atm, and 298 degrees Kelvin. Here, this would apply if all of my quantities were not at standard conditions, right? Now, we see also that this is tied to temperature, right? And we note that that temperature is actually tied specifically to entropy, right? Why do you think that's the case? Why is the temperature tied specifically to the entropy? Right, because temperature has a huge impact on entropy. Because remember that as we change phase, right, as we change states, we have big increases or decreases in entropy, right? And that also increases how much motion you have. So temperature is innately tied to entropy, which is why that's where the term shows up, okay? Now, so this is how we tie Gibbs free energy to these processes. Gibbs free energy, right, kind of, right, the math for it is beyond what we have to know, right, but Gibbs free energy ties back to the work component from our delta E equals Q plus W, okay, where delta G actually tells us the maximum amount of work you can get out of a process, or the maximum amount of work needed to put in to make a process occur, right, but delta G does tie back to that quantity, okay. But it does allow us to then look at this and then have a way to talk about whether or not a process is thermodynamically favorable. So if my delta G is less than 0, then what that says is my process is, I should have typed this out because I hate writing this, thermodynamically favorable. Meaning based on the energetics, okay, of my products versus my reactants, this process ought to go on its own. Okay, thermodynamically favorable. It ought to go on its own. It is basically spontaneous. Though spontaneous is not the word of choice. Thermodynamically favorable is. Okay, so that would mean I have, and I should be more specific here, it means negative numbers. Okay, specifically we mean negative values. When we have delta G's that are less than 0, right, so negative, it says that my process is thermodynamically favorable. When I have delta G values that are greater than 0, what that tells me is I am thermodynamically unfavorable, meaning that that process as written is not likely to occur without outside influence. Some energy has to be put in order for it to happen, okay? Because my products are higher in energy than my reactants are. Now, what that also means, right, is that going back to the stuff we talked about with Hess's law, right, means that if I have a process as written that is thermodynamically favorable, the reverse process is, ding, 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 by default, unfavorable, right? Because if it's in a negative delta G in one direction, if I flip it, it's going to be positive, right? Likewise here, if it's unfavorable in one direction, if we flip it, it would be favorable in the other direction, okay? Then I think that leaves us with what seems like the obvious part that has to happen in the middle, right? Delta G can equal 0. So what happens when delta G equals 0? Equilibrium. That means we are at equilibrium. Equilibrium means macroscopically there is no further change in my process. Microscopically, it means there's no further change in concentrations. No change in the concentration of my reactants, no further change in the concentration of my products. Okay? So macroscopically, it's where no further change is observed. Microscopically, there is no further change in the concentration of my reactants, no further change in the concentrations of my products, okay? And that's what equilibrium means. So when we say that delta G is equal to 0, we mean we're at that place, which means that neither forward nor reverse are favorable, okay? And note that this doesn't apply to the standard, okay? The standard process is always going to have a value. This mostly applies over here. And we're going to further describe and define those in a minute. All right. Another way to solve for delta G of a process, so one way is that if we know these two terms, right, we can solve for delta G using this equation. Another way to solve for delta G, just like we did for enthalpy and entropy, is we have our standard free energy of formation. Here, we are bringing back the formation term part, right, because this is the amount of energy, the amount of free energy, which again correlates back to work, okay, associated with a process. So if we think about this again is going to be just like the standard enthalpy of formation, wherein elemental things in their standard states at 298 are going to be 0. So for example, H2 gas at 298 has a delta G formation of 0 because there is no energy required to make this be what it is, right? That's just how it is. So anyway, we can use this to solve for delta G in addition to our other method of delta G equals delta H minus T delta S. All right. Stay tuned. We're going to talk about some more ways to discuss free energy in the next one. Thanks for listening. Be good, and I'll see you soon. Bye.